Okay, so let's continue with our introduction to field equations, and let's see if we can make any sense of the Dirac equation. So we're going to try to give a somewhat of a logical reason to want to have something like the Dirac equation, right? Remember, all of this physics at this point is poking and prodding through our axiomatic systems, looking for things that actually model nature. And so there's no direct line, right? As I said in the last lecture, right? There's no direct line from classical mechanics right into quantum mechanics, right into relativistic quantum mechanics, right into quantum field theory. I mean, there's a straight line in retrospect, right? As we look back at the history of the subject and the development of the subject. But if you're standing here, there's no obvious clue about how to get to here. And there's no obvious clue about how to get to here. And there's no obvious clue about how to get to here. You have to do a little bit of guesswork. And so guesswork is kind of the way this process works. On the other hand, if you have this, then you can definitely get to this, definitely get to this. And inside here, all of this is contained in limiting cases. But going this way is insight and the activity of geniuses and the accumulation of knowledge in well-regulated institutions that examine each other, that, the whole process of science and philosophy gets you here. Coming back, we're kind of basically what we're doing is we are going backwards. Even though it looks like we're going this way, and I'm claiming, okay, we started from classical mechanics, I'm doing prerequisite stuff, I assume you know quantum mechanics, now we're going to talk a little bit about this. It looks like we're going this way, but the only reason we have a path to walk this way is because people have already created this thing, and I'm actually going backwards. I'm just telling a backwards story backwards, right? Okay. Enough about that. Let's begin, and let's see if we can now introduce the idea of the Dirac equation. So we had this mind map, and the first thing I'd like to point out is a very astute observer noticed I had a sign error. I can't believe this error, too. I had a sign error in my classical Klein-Gordon field analysis, and the problem that I had was, it's a tricky little problem. It's worth seeing. Well, let me put it this way. It's not a tricky little problem. It's a stupid problem, but it's the kind of stupid problem that we all go through. And, if this was a course in a classroom, I'm sure somebody would have raised their hand and said, hey, you missed a sign, right? But the issue is taking the derivative of the Lagrangian with respect to the field variable requires taking the derivative of this with respect to phi, not phi dot, phi, not the gradient of phi, but phi. And this 2 comes out, it cancels this 1/2, and you end up with the negative m squared phi. And that's what I was carrying through the whole problem. The issue is, though, that I'm looking for in the Euler-Lagrange equations, I want to take this, I want the negative of this derivative. And that's what I failed to do. And so this sign in the previous lecture was sitting as a minus sign. And the ultimate equation ended up with a minus sign here, which is absurd, right? Absurd in the sense that if you know what the Klein-Gordon equation is, you know that there's no minus sign there. This is a positive number, that's a positive sign. And also, the other thing that made it truly absurd was that I had it correct over here when we did the sort of the relativity version of it, where we first quantized the energy momentum relation, and this was correct. So I had two different equations for the Klein-Gordon equation at the end of the last lecture. So this is the correct version, and the error was missing this sign right here. So before we discuss the Dirac equation, let's remind ourselves, this guy here from special relativity, it's the law, right? It's the rule. There's no reason why you would expect any kind of relativistic energy momentum relation to be different than this. This is the one from special relativity, and it must be obeyed by all particles, period, right? So when we create this equation, we're definitely saying that, this field variable which is interpreted because, remember, this is derived from the first quantization rule, right? We take the energy-momentum relation, we replace the energy with I, h bar, partial with time, and here we replace it with minus I, h bar gradient, right? So when we do that, we're hoping that this guy's going to come out and be a wave function, right? So we're thinking about this in terms of a wave function. But a wave function's still a field, right? It still is a scalar field. It has a value at each point in space. It's the interpretation of that value that is now different. You know, it's now not a classical quantity that can be measured. It is now part of a quantum mechanical wave function that has its own interpretation in principle. Now, the problem, of course, the famous problem with this is that interpreting this as a literal wave function doesn't work very well. In fact, it fails. And my understanding is that was recognized pretty quickly. I think the story goes that Schrödinger actually did this. This is sort of obvious, right? This is a legendary equation that's staring everybody in the face. So this notion of first quantization was the first, if you're going to try this idea of first quantization, of substituting these operators into something, if that's your plan, then this is where you would start because everybody knew this was true. Unfortunately, it didn't work, and so fortunately, he created the regular Schrödinger equation, which did seem to work, but is not relativistic. So they kind of put relativistic principles on the shelf and developed regular quantum mechanics. And they fully understood it wasn't relativistic. So I guess they decided, well, we'll have to come back and figure that problem out later and just work in a non-relativistic regime. So, but the point is that the fact that this has to be satisfied is an important piece of understanding how the Dirac equation surfaces. One other thing I'll say before we begin the Dirac equation is here I write down the Pauli matrices. I'm trying to be consistent with Peskin and Schroeder. This just is one of the, it's as far as I know, I'm sure maybe it's like a legendary textbook, really important textbook in field theory. Not necessarily the best for everything, but it's a great textbook to start with. And I'm trying to use all of its conventions. And I captured all the conventions here, but I just noticed that in my Pauli matrices, these subscripts actually are superscripts in the Peskin and Schroeder convention. And I actually wrote them as superscripts here, but I wrote them as subscripts here. So I'm going to fix that. And that is more correct. All right. So now let's now turn to, having reminded ourselves of all these facts, now let's turn to the idea behind the Dirac equation. We are going to do this is the most common approach, I think, to explaining why the Dirac equation is a thing. The idea is here I'm writing down the Klein-Gordon equation in full, right? I've blown up the partial mu part, right? And when you do that, you end up with this expression here. And I've collapsed these units, m squared, c squared, h bar squared, into just mu squared. So we have this guy. Now, what I'm going to try to ask myself is, well, first of all, this thing is a second order differential equation, right? And this is one of the problems with the Klein-Gordon equation. This is the Klein-Gordon equation. This title here is the Dirac equation via factoring is what this sort of section of the mind map is all about. But right here we have the Klein-Gordon equation. And the point is, if you were to solve this, you would solve for some function phi of space-time, right, which I write as phi of x. And in order to uniquely solve it, you're going to need an initial condition, which is a value of phi of x at some particular value x equals x prime, I guess, that establishing its value at t, x1, x2, and x3. And you also would need to know its first derivative, right? You would need to know, say, the value of the first derivative of phi of x, right? because you need two conditions really to establish the value of the wave function uniquely, right? You're trying to solve a second order differential equation. So you need two pieces of information. Now notice in quantum mechanics, you don't need two, you only need one, because it's first order in time. The Schrodinger equation is first order in time. And the Dirac equation is second order in time. Actually, so I guess the conditions you need are the spatial value of the wave function and its and the spatial derivative, the time derivative of the wave function, right, at two different times. But the point being that, or at two different conditions, right, in order to get it. So right away, the interpretation of the wave function becomes a problem because the understanding of a wave function is when I know the wave function at a certain time, right, the Schrodinger equation tells me how that wave function will evolve straight. I don't need to know the wave function and how the wave function is changing, right? I don't need to know that extra piece of information. So that's one problem, is this extra amount of information that you need to nail down psi if the whole equation is second order. And so I guess the way the story goes, and I don't mean to demean the history by saying the story goes, but I'm not a historian of physics, and I haven't read the letters and messages and all the original papers or anything like that. I just read I've like any other person who's learned the subject in the modern era, I read distillations of this stuff. So the story as I've heard it is that Dirac says, okay, let's try to make the whole thing first order, right? The non-relativistic one is first and second order in time, second order in space. Let's see, and Klein-Gordon doesn't work very well, and it's second order in time and space. Let me find one that is first order in time and space and find an equation for the wave function of an electron or a particle that is first order in time and space and make it relativistic. And so I'll solve this problem of relativity. And so what he sets out to do is he knows that the Klein-Gordon equation has to have something to do with this because it's a direct expression of relativity, right? It falls right out of this basic principle. And the only thing people know how to do is to first quantize, right? So he's saying, okay, what I'm going to do is I'm going to say that there are these numbers A, B, C, and D. And if I take a linear operator, just straight up linear operator, first order, linear operator, first order, meaning, and I have these arbitrary constants A, B, C, and D, and I square it, then I'm going to get the Klein-Gordon equation. And then what I'll do is I will take the square root of it, meaning I'll eliminate these little squares, and what's left over is going to be a first order equation where if this function satisfies that first order equation, it's definitely going to also satisfy the Klein-Gordon equation because this operator that drives the first order equation is just sort of the square root of this thing. Now notice, this is the Klein-Gordon equation, but I write it down as A, B, C, D, and I add this I here. But if you check it all out, this guy here, this is the same thing as this, right? If you, what would you do? You take this thing here, move it over there, you have a minus sign, multiply everything by -1, you get a plus sign there, those guys become plus, you get a minus there, but then I'm going to turn it into a square, so I take that minus and I drive it to be an I, and you see now we have the structure that I've written out right here. Okay, so this is equivalent. So now we got to look for these numbers, A, B, C, and D. And I emphasize numbers because, of course, they're not going to end up being numbers. So we think about this. We say, okay, here's this thing. I'm going to square it. It's going to equal this mass term, phi squared. Let's blow this up and see what we got. And when we blow it up, we just do the obvious thing. I mean, we're just squaring this quadnomial, I guess, making sure we keep track of this I a little bit. And we have this square term and these cross terms, right? The square terms are here on this diagonal, And then you have all these cross terms. And then the problem is okay, so this guy here has got to end up equaling this guy here. And that's a bit of a problem. I mean, we've already can see right away that this piece is going to have to correspond to this piece, that this b squared part is going to have to correspond to this, and this c squared part is going to end up having to correspond to this. Of course, this corresponds to that. And then the t squared part, that's this part here, is going to have to correspond to this part here. But that's all the parts, right? Which means everything else has to cancel out. Now, what you'll notice is that, again, just like I said before, I'm working backwards from knowing the answer. Because when I blew up this quadnomial, as I'm calling it, I guess, I'm keeping track of the order of things, right? A squared is fine, but when I do a times b, I do the ab, but when I do b times a, I leave it as ba. I don't say it's ab and I get 2ab. I don't assume they commute, right? And that's because I know that if I assume they commute, the problem doesn't solve, right? You end up with 2ab here, right? You end up with a 2 here, right? And the AC becomes a 2AC and the CA is gone, and the AD becomes a 2AD and that's gone. And you're stuck, right? You don't have a square root whose square is actually the Klein-Gordon equation. And so looking ahead, I know that, okay, well so you and me, we see this and we go like, well, okay, this is a failure. We move on and maybe try something else, or we become like biologists or something. But not Dirac, right? Dirac said, I think the problem is I need A and B to cancel with BA. And I do know something that could do that, and it's not a number, it's not a real number, it's not a complex number, it's a matrix. So A, B, C, and D have to be matrices, which is what he decided was the case. Now, the reason that this was so significant is because, okay, sure, matrices will get all these cancellations to work if you find the right ones. First of all, you say, well, matrices can make these things cancel, but can you find 4 matrices whose squares will give you this, and whose commutators whose commutators will cancel, which will cancel when they commute, and there are 4 of them. Can we find matrices to do this? So there's that question. But even if you did, then you end up with a matrix equation. And if you have a matrix equation, you're now going to be looking for an object that is a column vector that has the same dimensionality as your matrices. So phi ceases to be a wave function like we've always seen in quantum mechanics. It now becomes some kind of column vector. Now, indeed, by this time, it was already known that you could ad hoc add into quantum mechanics things like 2x2 matrices, right? 2x2 matrices, and you could add into the wave function a column vector of 2 parts with a function attached to it, and you would call this a spinor, right? That was already known, but it was totally ad hoc, right? It was totally ad hoc, meaning they just realized that if you did this mathematical thing and you now created this notion of a spinor field as a wave function, you could solve problems involving angular momentum, spin 1/2 angular momentum. But without that, it couldn't be done. But they just noticed it, and they added it in there as an assumption to the theory. The idea now is that this is different. If you can find these 4 matrices, and now phi becomes a column vector by its very nature, and remember, those 4 matrices are forced on you by the principle that you need to satisfy this, ultimately, this relativistic principle. So this relativistic principle drives you to ask this question: And the answer forces you to accept matrices, which forces this wave function to now be some kind of column vector. And I'm sure at this point he's like, well, I'm on the right track, because that might explain this ad hoc crap we've had from quantum mechanics. So let's go, right? This is going to be great. So right now we're kind of optimistic about all this. So what do we do next? Well, we look at, well, what are the requirements for these four matrices? And as I said before, they have to cancel, right? AB and BA have to be opposites of each other, and all of these cross terms have to cancel. So you have all of these requirements here. And then when you square them, you have to end up with 1, right? You have to end up with 1. So each one has to be sort of, well, the squares have to be 1, and they have to all cancel like this. So finding these matrices, well, that's the next thing we do. And immediately you might get excited about this, but then you realize, you know what? There are no 2x2 matrices that do this, right? There are no 2x2 matrices that will satisfy all of these requirements. So whatever this is, it's not going to immediately reproduce this ad hoc invention that saved quantum mechanics and made quantum mechanics really, really relevant. It's something else. It turns out the smallest size matrices that can do this, it turns out, are 4x4 matrices, which means this guy has to be a column vector of 4 elements, which means now we're talking about some kind of field that at every point in space-time, right? Every point in space-time, boom, there's some kind of structure that has 4 elements in it, right? 4 degrees of freedom, I guess you could say. And every point in space-time is assigned some value, some numbers, right? And these will be complex numbers, right? And there'll be 4 of them for every point in space-time. So you have this field. And we'll still call it a spinor field, right? Even though the spinors from quantum mechanics only had 2 dimensions, we're still going to call this a spinor field. And now the mission is to find these matrices, all right? So let's have a look at that question. So the good news is that there's a lot of matrices that satisfy this, and there are 3 sets that are typically used in the literature. And these 4 matrices, the common name, gamma 0, gamma 1, gamma 2, and gamma 3. So these are all gamma 1, these are all gamma 0, these are all gamma 1, these are all gamma 2, these are all gamma 3. And the difference is that they're different representations of these, what we're going to call these gamma matrices. But they all satisfy the requirements that we need to make all of this work. Now, there is a little bit of an issue between what I've defined as A, B, C, and D, and these gamma matrices, but we'll clear that up in a moment. The point is, these gamma matrices are the matrices that go into the Dirac equation, and there are 4 different, these are the 3 most common representations. In fact, the Dirac representation and the Weyl representation are by far the more common, and the Majorana representation is far less commonly used. However, it's a really interesting representation. I think I want to explore it a little bit in our Prerequisites series just to really get a good feeling on how the Dirac equation works. There is a simplified notation for these 3 representations, right? The Dirac representation, gamma 0, these are meant to be 4x4 matrices, right? Because each of these are 2x2 matrices, right? So there's 2x2, 2x2. So this clearly means the 0 matrix, the 0 2x2 matrix there. That's what that means. So likewise, this here means 1, 1, 0, 0. It's the 2x2 identity matrix. And this is the opposite of the 2x2 identity matrix. So this is a bit of a shorthand for how to write down these gamma matrices. Now you'll notice for the Dirac representation, right, these gamma matrices are very simple. You just have the Pauli matrices for the 1, 2, and 3 versions, and the 0th version is just a diagonal matrix. For the Majorana representation, it's actually, there is no super duper shorthand. you've got to express each one separately. But notice there's a certain amount of favoritism to the second Pauli matrix. And there's a reason for that. If you look at these matrices carefully, what you discover is that if you go back to the mind map, if you go back to the conventions, sigma 2 is the only complex Pauli matrix, right? It's the only complex one. So if you go down here to back to the Majorana representation, right? And you notice that sigma 2 is there. Now I have sigma 3 is real, sigma 1 is real, sigma 2 is complex. But notice I'm taking these real ones and I'm multiplying them by I, right? I'm multiplying them by I here. So now all four of these matrices, all four of these gamma matrices are complex. Here, that's not the case, right? Sigma 2 is complex, but the others are not. And the same is true for the Weyl representation. Notice the only distinction between the Weyl representation and the Dirac representation is in gamma 0, right? Everything, these guys are the same, actually. So these different representations work, and when you actually make contact with this material right here, you end up with the Dirac equation. And here it is. This is the Dirac equation. And if you square this Dirac equation, you will get the Klein-Gordon equation. And you will get the Klein-Gordon equation because these Dirac matrices, there is a good important point there. You get the Klein-Gordon equation because the Dirac matrices obey very specific rules. And these rules, these anti-commutation rules, right, are what are so important to allow this squaring to give you the Klein-Gordon equation again. And what's interesting now, these are typically called, Dirac matrices. However, that's different. These are all then Dirac matrices, but these are Dirac matrices in the Dirac representation, right? So I want to make sure the language is clear. These are Dirac matrices in the Dirac representation. These are Dirac matrices in the Majorana representation. And these are Dirac matrices in the Weyl representation. And the Weyl representation, by the way, is sometimes called the chiral representation. And this is the one that's used by Peskin and Schroeder. So we'll probably be leaning into this one a little bit more than the others. Although like I said, we're not doing field theory. We're just sort of doing the prerequisites. So I don't, we'll spend some time comparing some of these. I think instead of just going through the solution of the Dirac equation, which we eventually will, I want to compare with the Majorana representation. And so I'm not sure which representation we'll use to solve it. It becomes kind of unimportant at that point. It's just understanding the nature of the solution really doesn't depend that much on the representation. The Majorana representation can be a bit tricky, though. So, in my opinion, and mostly because we're unfamiliar with it, right? It's like I said, my first textbook that I ever learned from used this representation. Peskin and Schroeder uses this one. Okay, so this is now the Dirac equation. And now it's talking about a 4-component spinor field called a Dirac spinor. And this Dirac spinor object, each of these values has four components, right? And each of these things, right, psi sub 1, for example, is a complex number, right? It's ultimately a complex number. So it's a 4-component object of 4 complex numbers applied to each point in space-time, right? So every point in space-time, because that's what a field is, right? It's a Dirac field, so at every point in space-time, it's given one of these things. And the whole Dirac field is written usually as psi of x, and its evolution is, its equation of motion is going to be this guy right here, the Dirac equation of motion. Now, a really annoying confusion is there's 4 components, right? There's 4 components. Space-time has 4 components, right? And so you've got things that have 4 components that are unrelated as far as you should be worried about now. Spinors have four components because, I guess the way we want to think about it in this line of thinking is because the representations we're using for these gamma matrices are 4 by 4. It's the smallest one that's available. 3 by 3 doesn't work, 2 by 2 doesn't work, and scalars don't work. 4 by 4 works. It's the smallest one, so we're going with it. This forces the wave function that we're seeking to have 4 components. But notice that why are there 4 Dirac matrices? Why are there 4 of these guys? Well, you go back up here and you realize, well, we threw a coefficient in front of each of these partial derivatives. And there's one of these for each direction in space-time. 1 for the time direction and 3 for the space direction. So because space-time has 4, should I say degrees of freedom? 4 coordinates, right? The space-time has 4 coordinates and therefore 4 operators, energy and momentum. We end up with 4, what we were looking for to be numbers, and to discover that they're matrices. So we end up with 4 matrices, 1 for each direction in space-time. And so we give them an index to reflect that, right? And we write down these Dirac matrices with an index mu. This index mu is, in fact, a space-time index. This is a space-time index. And you can take it seriously as such, right? You can raise and lower it, and you sum over it. You sum over it with other space-time indexes. So you write gamma mu partial mu. You mean gamma 0 partial 0 plus gamma 1, gamma 1 partial 1 plus gamma 2 partial 2 plus gamma 3 partial 3. You treat it like a space-time index. However, the Dirac spinor, these components, right, they are not associated with space-time indices. These are a totally different index. It's coincidental that it has the number 4, right? Well, from this point of view, it's coincidental that it has the number 4. At some deeper level, I'm not going to comment. But the fact is that it has the number 4 because this 4 by 4 matrix pops out as the smallest matrix to satisfy our requirements, right? But it's not; these are not space-time indices. So you will never see anything like some vector, in this case a contravariant vector, psi mu. You'll never see that because you don't index the wave function with a space-time coordinate. In fact, I'm going to erase that fast because I don't want anybody to think otherwise, right? So usually when you see psi, you very rarely break it up into psi 1, psi 2, psi 3, and psi 4 and talk about them independently. Very, very rarely. And so whenever you see psi, you immediately think of a 4-component object. And you can never, if you do see psi with some sort of index here, that index can never be summed against a space-time index like that. You'll never see something like that because it's just a different index. And this is a major problem in QED, a major problem for new students in QED, is you'll see indices all over the place, and they represent indices of totally different natures. And you have to keep track. What is a space-time index, right? Where are the space-time indexes in your problem? And where are the internal indices that represent the components of the spinors? And they show up, and the more complicated you get in the field theory, the more different indices show up. And it becomes, it becomes quite a challenge to keep track of them. But if you do keep track of them, you never make a mistake, right? Anyway, okay, so there you have it. There we have our Dirac equation. And the derivation is as I've expressed it. If you actually go to some of Dirac's original work or some older treatments of this, what you end up seeing is, let's just start with a linear equation. Let's just invent a linear equation that satisfy that when squared gives you the Klein-Gordon equation. So you end up seeing these alpha matrices and beta matrix, and you know, it's the same analysis, right? You just square this thing, and you're still looking for matrices that end up satisfying the exact same rules we just found. But there is this thing where you talk about Dirac's calling these the alpha matrix, and the time one ends up being, well, then there's this beta matrix. And so just be aware that there's this other sort of notation out there when you try to find your own version of this in whatever textbook you're favoring. Okay, so that's it for the Dirac equations introduction. And so now we've studied the Klein-Gordon equation and the Dirac equation. So the next thing we're going to do is we're going to look at Maxwell's equations, which are also field equations. And we're going to understand how Maxwell's field equations have to be massaged into a form that you're very familiar with. You have to become very familiar with a different form of Maxwell equations to make any sense of field theory. And so before we go solving the Dirac equation, the Klein-Gordon equation, I'm going to revisit Maxwell's equations, and we're going to talk about Maxwell's equations in reciprocal space. And that will be our next lecture. Okay, so I'll see you next time.